Today what we will do is we will classify the aeroelastic problem as in a general fashion. Okay, and solutions. The various types, how do we solve? We will use operator form because we said that when you apply a load, there is a deformation. That means you have a structural operator which acts on the deformation to give you the load. In the sense, we will use the structural operator acting on some deformation, which I am going to call it in a general fashion Q, which is a generalized coordinate. This is going to be the external load, which is a generalized force. Okay, this is the form of the aeroelastic equation. But now, what are the various types of loading which we will have in the aeroelastic equations? If you look at it, we will have loading, one from aerodynamics and another from inertia, and the third some other external, which can be some dynamic or external loads, you can call it. Now each one of them we are going to put it in this, I will call it as Q aerodynamics, this I will call it as QI, this is some QD, this is the symbol I am representing. Now if you look at the aerodynamic load are functions of the, so I will use a Q. Aerodynamic load is a function of the generalized coordinate, or you can say the deformation of the structure. Similarly, inertia I will use I, which is also a function of Q. Now I substitute back here for Q is essentially QA plus QI plus QD. These are the, now I put all of them in operator form. I will have structural operator Q equals aerodynamics is A loads, inertia plus QD. Okay, this is the, that means all aeroelastic problems are brought under this type of you can say symbolic representation in operator form. Okay. Now the question is, these operators can be differential operators or algebraic. If you have in different form, it could be an integral operator also. It's possible. But then, what are the characteristics of operators? We saw the self-adjoint operator earlier. Okay. And for that we got the solution, etc. Now we will just put it in the classification of this, whether we can take inverse like structural operator operating on the structural operator. Okay. This is but please, this is this condition will be valid only under certain special cases. That means they are commutative. Okay, mute, that is AB is equal to BA. It is possible that only when you satisfy certain boundary conditions, I'll give it as a homework to you to show that what should be the condition which this is valid for the same problem which was discussed in the class. Okay, structural operator operating on it in 1. This you put it. Now what condition that this will be valid? But in general, if I take inverse of this, because I need Q, Q will be structural operator into A, structural operator inverse into I. Now I cannot put, this is not valid, the commute. This is not, they don't commute. Okay. Therefore, each problem you have to solve separately, and we will learn the methods of solution. Okay. Now we will classify problems. This is the general under different categories. Okay. If we classify, suppose if I neglect inertia, this static aeroelastic problems, they can be of the form take dynamic load, I put it, but then UD essentially it can be some aileron part. That is why I put a D here, even though I put it as a dynamic earlier. Okay. Here I put it is a dynamic load. This situation here it can be due to surface motion, which is control surface motion is independent of the generalized coordinate of the wing deformation. Okay, that is why I put it. This type of problem is basically control effectiveness. Okay, and control reversal, etc. They will come. You understand? But if I put this 0, that is, this is 1, the other one, if I set that QD 0, I put like this. Equals 0. Problem looks like a problem type of thing. Okay, but it's all operators. I'm just saying that. Now this is a divergence problem. This is similar to buckling, which is like an eigenvalue evaluation. Okay, so this is divergence problem. Wing divergence, divergence of elliptic surface. Okay. Now if I take inertia into account, this is dynamic. Under this, you will have the full equation. There is no Q minus AQ minus I Q equals QD. This is response to burst or any dynamic load. Okay. QD is, it can be landing, because when you land there is an external load comes in, impulse type of. But if I neglect QDs, that is then this problem becomes our zero. This is again like a similar to another eigenvalue type of a problem, but then this is a stability. You can call it dynamic stability or flutter. Okay. Or flutter type of problem. Okay. Now you see our general equations in this fashion. Only thing is a sub part of the equation represents a particular problem. That's all. So the whole idea is now first formulate the equation of motion or equation for representing the aeroelastic problem, then classify them what type of problem you are solving. It will give you static aeroelastic issues, dynamic aeroelastic issues. And this is where we studied about the various type of operators. Okay, adjoint operator. If it is a not self-adjoint, because self-adjoint operator is what we saw. If it is non-self-adjoint, how do you solve? Okay, that part we will do it as we go along the course. Now the question is, we saw in the vibration problem that beam vibration only for a very special case we have closed form solution. Very special case, that is constant uniform properties everywhere. But if in real life the properties are varying, then how do we solve? We cannot get exact solution. You have to resort to only numerical or approximate solutions. Now, how do we get these approximate solutions? That is this part. First is the equation is this part. You have formulated the equation. Now, how do you get the solution? Okay. Basically, I would say there are two stages involved in the solution procedure. Two steps. First step is you say that you have an infinite degree of freedom system because it is a continuous system. You have infinite degrees of freedom. You are not going to solve infinite degrees. So you have to first convert the infinite degree of freedom system into a finite. That is the first step. Okay. So I will write here. The two steps are, one is reduction of the, reduction means you are basically making approximation, infinite degree of freedom system. You first put it into infinite DOF to finite degree of freedom system. This is the first step. You reduce it. Now this is where how many finite, when you say how many you should treat it. Okay, this question will arise. That's why I said in the case of a rotor blade, we take about 8 modes. Okay, 3 one side bending, 2 in the other bending, 1 torsion and axial, like that. Whereas in the case of an aircraft wing, actually some industry calculations they may take about 40, 50 or 100 modes. Maybe 40, 50 modes. Is it really necessary to have higher modes? That depends on how accurately you want your results predicted. Okay. So this is the reduction of an infinite to finite. Once you reduce it, this stage, the equations will become, because in the infinite degree, it will be partial differential equation, because you have distributed loading. We all saw in the vibration, it was a partial differential equation. Later we did the separation of variable, we converted into eigenvalue problem. And then we use the orthogonality principle to convert to ODE, ordinary differential equation. You saw last class. So when I convert to finite degree of freedom system, the equations can be algebraic algebraic in of static aeroelastic problems. Static aeroelasticity. But and it will be ODE, ordinary differential equation. Okay, ordinary differential equations in the case of dynamic aeroelasticity. Okay, but you know how to solve algebraic equation, but they will all be coupled. You can say coupled algebraic equations or coupled ordinary differential equations. And then comes the second stage is the solution. Solution of this finite degree of finite DOF system of equations. Okay, equations. This is the next part. So I first reduce it, then I go and solve. This is standard technique. There is nothing special about this. Because if it is an algebraic equation coupled, what you do, you take a matrix form, you take inverse or something, and then get the solution. If it is an ODE, you know, it's a system of ordinary differential equations. You can take the solution for that. Key is how do we reduce from here to here? Okay. In the step 1, there are what type of approximate techniques? I would say what type of techniques are used in approximating infinite to finite. Okay. So that I will describe now. So is it clear? That is the technique that is adopted from reducing here to here is what I am going to say. This part is, it is known. Once you get an algebraic equation, you know how to get the solution. Okay. Now there are 4 types of approaches. One is collocation. Collocation method or collocation technique. Okay. This is the first technique. Okay. I may put it 1 minute. This is, I'll take this part. Yeah. You may call this direct collocation. Okay. And number 2, you have collocation with generalized coordinate and assumed modes. And number 3 is Galerkin's method. And the last one is Rayleigh-Ritz. Okay. Rayleigh-Ritz approach. All right. These are the 4 approaches which we use, but I'll just briefly describe these methods. Okay. The first one is direct collocation. Suppose you have a wing which is okay. This is your x-axis, this is your y-axis, this is your z-axis. You have a wing. Okay. You make the wing into a grid. Okay. Okay. Several grids. You call these as any point here. These are nodes. You may call them nodes or anything. Okay. Now I apply a load there, which I call it, this is the jth node, this is the ith node. The load is, that is the external load, I am calling it, applied at this location, and this is the deformation, which I call it as W at I. Okay. That means I have my equations, continuous system equations, but I am not going to solve a general solution. I will only solve if I take some 100 points. You try to solve only at those 100 points. That means I am dividing my structure into 100 or 1000 or depending on the number into the nodes. Then your equation will get converted into in this fashion. This is direct collocation. What will happen your equation? Your equation will be simply your structural operator minus, this is one operator, aerodynamic operator, inertia operator. I am assuming the system is linear, so I am taking it out. This is acting on my Q. The Q's are W. That means I. These are all N by N system. N by N. This is equal to my generalized force, which here I put it as ZD. They will act at ZD. I won't put an I here. I am putting it because this is what I am having. This Q is a vector which contains Q1, Q2, etc., Qn. Please understand, these Q's are nothing but my W1, W2, Wn. And this Zd, again it will have external force, Zd or Qd, you can call it. This is basically the external, whatever dynamic load. If it is 0, that will be 0. You can take it. Okay. Now, this is pure equation in this form. N unknowns, N equations. Okay. And you just solve this equation. But I am taking it as though they are linear. I have taken it out and done things like that. Okay. This is called the collocation. That means, this is like I told you, you have the influence coefficient. You formulated, right? You put a load in one place, you found out the deflection at couple of locations. That influence coefficient matrix, which you formulated. And those are these matrices. The influence coefficient, you put a load, deflection, load, deflection, load. Here this will become like a stiffness matrix, because stiffness into deflection is force. Okay. So it is a stiffness influence coefficient. That flexibility influence coefficient or stiffness influence coefficient. Now you formulated that, but this is one type of formulation. That means I am trying to satisfy my equation only at n locations on the structure. Okay. This is one form of, that is the direct collocation method. All right. Now, if you take the next method, collocation with generalized coordinates and assumed modes. Please understand, this is a little different from the first direct collocation. Direct collocation is you simply take your equation, put the node. Okay. You formulate all these influence coefficient matrix and then combine them. Any external load you will have this. Okay. But you may ask, how do I get these things? That is another question. Okay. Next we take the now this is again I am using the same thing only, but now I will not put in this fashion. I am going to represent W is in this direction, which is a function of x and y because it is a planar. So, right, this is the technique 2, collocation with generalized coordinates and assumed modes. Here I am writing it as I running from 1 to n, gamma I y into, maybe I will use q. Okay. But please note, if it is a function of time, this will become like this. This will be in this fashion. I running from 1 to n, gamma I x comma y q I t. Okay, please. So, okay. If it is a static problem, it will be like this. If it is a dynamic problem, this will be in this fashion. That means what I am trying to represent is I am assuming the deformation to be a summation of some modes. These are assumed modes, gamma I assume them, but what they should satisfy. Okay, this is a question. They must satisfy your boundary condition because we are going to substitute in the equations. That is a different later. So, you must choose the functions or the assumed modes. They must satisfy your boundary conditions. All the boundary conditions, both geometric as well as natural boundary conditions. That is very important. And number 2, you are going to substitute, if it is a differential equation, you are going to substitute this back in the equation. So, they should be differentiable also. Okay. So, these are important. Now, you see this is a little different, but my unknowns are qi. Okay. This is essentially like a separation of variables. Okay. And the qi's are my generalized coordinates. Now, these are assumed, qi's are generalized. Now, what I will do? I will go substitute this in my aeroelastic equation, and then I try to satisfy this only at n locations. Okay. That means n points I must satisfy. I will not be satisfying everywhere. So, I can make a grid like this, and then I will write that equation here. So, you will have, when I substitute this in the aeroelastic equation, it will be I running from 1 to n. You will have structural operator, aerodynamic operator, inertia operator operating on, because I, you will have gamma I Qi, right? Summation is there. This is equal to external load. Your external load, you may call it ZD, which is what this load is, any dynamic load or control surface load, whatever you may call it. Now, I need to form, I don't know, this, okay, QIs. How many QIs I have? I have n QIs. That means I go and satisfy this equation only at n points on the wing, n points on the wing. Like in the earlier case we fixed grid, same way you do the grid, okay. N points if you satisfy, what will happen? I am choosing this point, these are n. Now here this will be x I, y I, that is the location, right. So I go and then write this in a very general fashion. Maybe I erase this. My equations will be written as summation I running from 1 to n, structural, aerodynamic, inertia, you put it here, gamma I at various locations. So I am going to change the location with the subscript xj, yj and qi equals zt which location I am looking at the location j. Now j running from 1 to n, okay, you follow. Now I am actually taking the load at jth location, finding essentially the deformation at the jth location, okay. But this is due to various QIs, every QI will come, okay. Now you form n equations and solve for this QI. Once you get the QI, you can substitute back here and get your W, okay. If it is a, that is why I said static problem, you will get algebraic equation, static aeroelastic problem. If you have a dynamic, this will become a ordinary differential equation, okay. Now this is the direct, I would say, what is the assumed mode. This is also collocation with generalized coordinates and assumed mode. There is a little difference between direct collocation and this, okay. The next technique is the Galerkin method. I erased this part, but please understand, all of them, they will have some link how the problem is approximated, okay. Because next I show the Galerkin method, which will look again here also. I am starting with W x comma y, this is 3. You can put t also. If you have t, you will have t. If you don't have time, you will have only that gamma I qi, I running from 1 to n. This will be a function of time. If it is a static, t will be gone. Now here again I am choosing, okay. Please understand, this is a little different from the method which I mentioned earlier. You take this, you go and substitute in your equation, okay. That means when you substitute in your equation will be summation I equal to 1 to n. You will have structural operator minus aerodynamic operator, inertia operator into gamma I qi. I am just substituting for the deformation directly. Okay. Now this is equal to the loading, whatever the generalized force. So I am subtracting the right hand side to the left. Please understand, this is now over the entire domain, because these are all fully is a function of x and y. This may be differential operator, etc. You will get a differential. But then at every point, if you do it, because ZD is also a function of xy, because this is a generalized force, you can say. The generalized force, when you get it, what will happen is, this will give you an error, because it is not going to satisfy. This is assumed. When I substitute in the equation of motion or the equation of the system, it will not satisfy exactly. You will have a error. Okay. Now the question is, you want to, this technique, this is a 1913, it was proposed. He said that, okay, I want to find out gamma I, right? Such a way that the error should be, that's all. You can say the error should be minimum, but there is no, he just, you can choose. What he did was, that Galerkin technique itself, it's like he said that this is, you know that this is a function of x comma y, because every point you will have an error. Okay. He said error is orthogonal to, that means error x comma y gamma I d domain, or you can say d domain, this is the O. Now you can say gamma I or j, you can use any one of them, it does not matter, I running from 1 to n. You can use gamma j also. If you want to put it, you can maybe, because when I am doing that, you can use j itself, that would be better. Where j running from 1 to n. Now what I have done is, this is the technique, is orthogonal to the assumed shape function, this one. Okay. Now you understand, these functions must satisfy my boundary conditions, technically all boundary conditions. Okay. Geometric and natural. That means those functions satisfy my boundary conditions is good. When I substitute in my equation, they are not satisfying it. You get an error, which is everywhere there is an error. I want the error to be minimum. And the simple technique is error minimum. He says that error is orthogonal to this. Please understand, it is not a minimization he is showing. He has shown that this is orthogonal to this. And if you do that, your equation will become, you will get essentially n equations, because you will put it as summation I running from 1 to n. You will put, this is an integral over the domain, that is all. I gamma I qi gamma j d domain equals integral, this is over the domain z d gamma j d domain. Now j running from 1 to Now you see, you will get n equations and you just multiply. These n equations, you solve them. Okay. So this is how you, like I said, infinite degree of freedom system, how are you representing by finite freedom? Now the question is how many modes you assume, that is your choice, your convergence. You can take 1, 2, 3, 4, keep on solving every problem and then see how my results are. Okay, you can stop at the point where it has converged. This is Galerkian approach. Now the next most widely used is Rayleigh-Ritz. Okay, but Rayleigh-Ritz, you start with, again I will briefly describe that part. Rayleigh-Ritz, you don't go and use your, this is the fourth approach. See, till now what we have used is, we use the equation of the system, that is structural operator, aerodynamics, inertia, all those are obtained, and those equations we have used. Now in Rayleigh-Ritz, you don't go and then start using there. Okay, what you do is, you start from, you actually use Hamilton's principle, or you can use Lagrange's. But starting point, like if you say, very general case I am giving, every point has a u which is a function of ui, qit, I running from 1 to n. Because these are UVWs, I am writing in a very general fashion, so that please understand this is not, this is a very general Rayleigh-Ritz approach. Vi, Qit, and W is again, please understand, you see all of them have similar expression, where u is a function of x, y, z, t, because these are displacements, u, v, w are displacements. If I don't have this, only w. Okay, you see this looks similar to what we assumed. Everything looks like a assumed mode approach. All of them are assumed mode only. But only thing is, now this wi, what condition I should have for this? It is enough if they satisfy my geometric boundary condition. Please understand, that is the key. Whereas in the Galerkian and all the other approaches, they have to satisfy all the boundary conditions, both geometric and natural. Whereas here, the condition is, it is enough if they satisfy geometric boundary condition, and of course they should be differentiable, that is important. Now you write your kinetic energy of the system. Kinetic energy, that means you are formulating your equation either by Lagrange's or by Hamilton's method. Please understand, you are starting from the beginning, writing energy expression, kinetic energy, strain energy, external work done, apply directly Lagrange's equation, or you can apply Hamilton's, any one of them, and you will get the equation of the system. Okay. Now this is summation I, summation j, both of them 1 to n. You will have a volume integral, because I am using the whole structure, density into ui, uj plus vi, vj plus wi, wj into qi dot qj dot dv. Okay. This expression I can write it as mij qi dot qj dot. Okay, because the integral is over the domain, the volume, because these are all only functions of x, y, z, ui, vi, wi, like we used earlier. Okay, whereas u is a function of x, y, z, t. This is also x, y, z, t, similar to that. Okay. Now you have the expression. Next you go and write strain energy and then the external work. So you will write the strain energy expression, you will get always u. Strain energy will be, u will be a function of your q1 to qn. That's all. Okay. That is the general expression. You have to substitute these deformations, you know strain energy expression, substitute them and integrate, you will get the strain energy, which will be only a function of the generalized coordinate qi. Okay. Now external, this will be, if it is a surface load, you assume that f dot dr, which is over the surface, f is fx, fy, fz. You take a dot product with respect to all of them, u, v, w, you will get fx ui. This is summation over the surface, okay, fx ui plus fy vi plus fz wi into qi ds. This is I running from 1 to n. This you can write it as summation I 1 to n capital qi lowercase qi. This is my generalized force. This is my generalized coordinate. Now you can directly go apply Lagrange's equation, because you know the expression for kinetic energy, strain energy and external, or you can use Hamilton's principle. Okay, you can use any one of them, and if you use Hamilton's, I'll just write that part. It really doesn't matter. Now you see the application of either Lagrange's or Hamilton's, because I have the expressions, kinetic energy, strain energy, external. So my Hamilton's principle, if I use, that will be delta T1 to T2 T minus U plus W external dt, this is 0. So you write each term separately, and then you will have integral T1 to T2 delta T dt. This is actually, you integrate by this part, integrate by parts. When you do this, is actually a quadratic expression. So what will happen is 1/2 will go off, and you will have your, I will directly write that expression, because this will be like summation I running from 1 to n, summation j running from 1 to n, mij qj dot delta qi. This is in the limit T1 to T2, then minus summation I running from 1 to n, integral T1 to T2, summation j running from 1 to n, mij qj double dot delta qi dt. Okay, this is what you will have if I integrate by parts. You know that time t1 and t2, my variation in the generalized coordinate, that is 0. So this term is 0. So this term directly goes to 0, leaving behind only this term. Similarly, your strain energy expression you will write delta of integral delta u. This is nothing but you will have summation I running from 1 to n delta u by delta qi. Okay. And external you will have delta w external dt t1 to t2, you will have again t1 t2 summation q I delta q I dt. This is I running from 1 to n. Okay. Now you have to combine, put it in this. You say all my delta qi's are independent. Therefore, if I substitute in this, you will have your equation t1 to t2 summation I running from 1 to n. You will have minus of I, sorry, there is no I, yeah, minus, I will put it here, j running from 1 to n mij qj double dot, that is this expression. Okay. Then I have to use minus this, that will be minus delta u over delta q I. Then this is the plus, you will have plus q I, delta q I dt is 0. Okay. Now, since all the delta qi's are independent, they will be 0. I will write my equation like this. Summation j running from 1 to n mij qj double dot plus delta u by delta qi. I will write it like this. This is also a quadratic function of the generalized coordinate. So I am going to write it as some stiffness matrix, okay, into q. That is how I will write it here. J running from 1 to n kij qj. So please understand, I am taking u is a quadratic function of qi. That is, the strain energy is a quadratic function of the generalized coordinate. When I do that, I will get this form, which will be again summation kij qj. This is because I have taken minus sign one side, so the right side will become qi. Now I runs from 1 to n. Okay. This is what my equation. I can put it in matrix form, which will be like m q double dot plus k q equals q. Okay. This is the n by n system. Now you can get the solution. So you know that m and k represent the mass and stiffness matrix of the system. Q is the generalized force. Once you get the q, you can go back and then substitute in your deformations. you will get all the deformation of the system. Is it clear? Now, unless you solve one problem, okay, by all these four techniques, very simple problem, all these four approaches, you can do one thing. You can take a cantilever beam, which is a representation of a wing. Take a beam. I am just saying, I am not going to solve, I am just saying that. And you have some distributed load which you may put it like a wing loading kind of a thing, and then apply all these four methods and get the just a static problem, deformation of the beam at any point, okay, using direct collocation, assumed mode, collocation with assumed mode, then Galerkian, then Rayleigh. Okay, all the four techniques. All right. Of course, I would like to mention a few points here. In the sense, the Galerkian and Rayleigh rates will give same. They are same if the operators are self-adjoint. Okay, that is the key. Now you understand what is the self-adjoint method, which I was telling, self-adjoint operators and other things. But if it is not self-adjoint, then these two will not be same. Okay, in which case you directly go and use Galerkian method. Galerkian method, not Rayleigh. You go and use the Galerkian technique for a wing divergence of a swept configuration. Okay, because you derive the equation and then apply Galerkian technique. So you see why these operators, when we want to say is it self-adjoint, non-self-adjoint, why this become too mathematical, is because of the solution technique. And you say that, hey, if the operators are of this type of form, then they have this kind of a solution. Now you have seen we have reduced the infinite degree of freedom system to finite degree of freedom system. Static aeroelastic problems will be algebraic equations, whereas dynamic aeroelastic problems will be ordinary differential equations in the finite domain.